phase diagram of matter depicts phases and phase transitions, which takes place when you change an external parameter, such as a temperature or a pressure or a chemical potential. The one on this left-hand side is the phase diagram of water. Pressure is plotted as a function of temperature. It is one of the most widely studied and precisely known phase diagram whose underlying interactions are electromagnetic, one of the 4 fundamental interactions in nature. It's part of the textbook. And what we are trying to do is to study the phase diagram of QCD matter. QCD is quantum chromodynamics, the theory of strong interaction, another one of the 4 fundamental interactions in nature. This phase diagram, which is temperature as a function of baryonic chemical potential, is largely conjectured. It's unique in the sense that other strong interaction systems can be part of this phase diagram. We need accelerators, as you will see, in order to access these phase diagrams. And the goal is to see if we can make it also part of the textbook. One of the exciting things to study this phase diagram of matter is to come across emergent properties of matter. For example, in condensed matter system, when you look at strongly correlated matter, we saw the emergent property of strange metal. That was made possible when you study the temperature versus doping of the system. And the experimental techniques one make use of is the angle resolved photoemission spectroscopy, where you have an incident photon on the matter and you look at the scattered electrons, momentum, and energy. The question is, can we do similar study of condensed matter of QCD? Well, we can do it by changing the temperature and sort of what is called as the baryon doping, by changing the baryonic chemical potential. That's just adding a baryon to a system or removing a baryon from a system. In fact, studies have reflected an emergent property of such a strongly correlated QCD matter in terms of perfect fluidity. We would need accelerator-based experiments, as you will see how it gives us access to the phase diagram in the next slides. We need colliding energies going from LHC, RHIC to future facilities at FAIR, NICA, and JPark. So one of the goals of the heavy ion collisions is to study the phase structure of this QCD phase diagram of temperature versus baryonic chemical potential. There are 2 distinct phases. One where the relevant degrees of freedom are quark and gluons of the quark-gluon plasma. The other where the quark and gluons are confined inside hadrons, the hadron gas. The QCD transition at 0 baryonic chemical potential is a crossover as per lattice QCD calculations. At large baryonic chemical potential, it's expected to be first order. The point where it ends is the critical point. So these are the various phase structures which we are looking for in heavy ion collisions. How do we access the phase diagram? We saw from the particle yields and its explanation using a statistical thermal model that the chemical potential and the temperature changes as we change the collision energy. Hence, by changing the collision energy, we can change the X and Y axis of this phase diagram and have access to it. Then we can study the properties of QGP and hadron gas, the nature of the transition, and search for critical point. Now, in strong interaction, there are 3 conserved quantities: baryon number, charge, and strangeness. It's the baryon number which we are able to vary appreciably through heavy ion collisions, and hence we come across this 2-dimensional familiar phase diagram which can be experimentally accessed. Now let's see what are the results, which interesting highlights which has come out from the top RHIC energy of gold-gold collisions at 200 GeV center of mass energy. That will set the stage for our goals of the beam energy scan program. We have seen the phenomena of parton energy loss, or what is called as the jet quenching. The observable is nuclear modification factor, which is a ratio of yield of particles in nucleus-nucleus collisions divided by yield of particles in nucleon-nucleon collisions appropriately normalized so that at high PT, if this ratio is 1, the nucleus-nucleus collision is a simple superposition of nuclear-nuclear collisions. If it's less than 1, then we have this jet quenching effect or nuclear medium effect. Here is a summary of some of the results of nuclear modification factor as a function of the transverse momentum of the particle. What you see here is the values for hadrons like pi0, charged pion, eta, and phi. The ratio is suppressed by a factor 5 from unity. For deuteron-gold collisions, where we do not expect a hot and dense medium to be created, this value is close to 1 or slightly above 1. For particles which undertake electromagnetic interactions like direct photons, their values are around unity. So this suppression of high PT particle production in nucleus-nucleus collision relative to PP collisions has been attributed to jet quenching effect or formation of a hot and dense colored medium. Theory calculations suggest that the energy loss has 2 mechanisms, through radiative process and collisional process. Another important finding from the RHIC top energy is the partonic collectivity. V2, which is a measure of collectivity, is plotted along y-axis. I will discuss this later in the beam energy scan results. This is plotted as a function of transverse momentum for light quark carrying hadrons, protons, and pions, and strange quark carrying omega and phi. Remember, the phi and omega are multi-strange hadrons. Their freeze out is quite early and have small interactions, cross sections with hadrons. Hence, their equally large collectivity reflects that a significant amount of this is coming from the partonic phase. You see some distinct features. Below 2 GeV of transverse momentum, there is a mass ordering, which is consistent with hydrodynamic-like behavior. And above 2 GeV, you see this baryon-meson ordering. This has led to the discovery of number of constituent quark scaling. In fact, measurements from STAR, which involves charm quark like in D meson, also shows substantial collectivity. And when we have V2 divided by number of constituent quarks, which is 3 for baryons or 2 for mesons, plotted as a function of transverse mass minus mass of the hadron divided by constituent quark, they line up in one curve, suggesting this number of constituent quark scaling or partonic collectivity. So these were the highlights at the top energies. Then we are able to obtain the properties of QGP, and this needed close collaboration between experiment and theory. This is sort of an early summary of how the experiment and theory worked hand in hand to define properties of this medium. For example, on this left-hand side, we have measurements related to jet quenching and theory development. This led to the defining the stopping power of the medium, which is of the order of 2 to 10 GeV square per Fermi. Then using the collectivity measurements and development of relativistic hydrodynamics led to obtaining the property of shear viscosity to entropy density, which is of the order of 1 to 2 times 1 by 4 pi. And this value turned out to be the smallest compared to the known fluids, and hence we have this emergent property of perfect fluidity. Measurements associated with charm hadrons led us to infer about the diffusion coefficient, and the values of diffusion coefficient times 2 pi t to make it dimensionless were of the order of 1 to 10. So we were able to extract properties of this deconfined state, which we created at RHIC top energy. Then that led us to the goal of the beam energy scan phase 1. This was proposed by Starr in this public note, and there were 2 ideas to look for. One is, just now I discussed about the phenomena of QGP. We were looking to see if this phenomena turns off as we dial down the beam energy from top RHIC energy to lower energy. The second was to look for signatures of phase transition and critical point. These 2 labeled as A and B, we were able to also provide the observables which would be sensitive to this set of observable A to the turn of phenomena, the energies and events that we estimated that time, and set of observable B sensitive to equation of state and critical point fluctuations are listed in blue. This was presented to the program advisory committee, and they first said that we have to demonstrate that the RHIC accelerator can deliver beam at lower energies, and the detector can take successfully data at lower collision energies. So we were given a test run at 9.2 GeV, gold and gold collision center of mass energy, 9.2 GeV. So at this energy, the colliders showed that they can have successful operation. And here is an event display of a typical gold-gold collision in the star TPC. We were able to collect 3,000 good events. The data taking was about 5 hours. And through these events, we were able to make measurements of observables which are related to bulk properties, such as d and dy, V1, V2, HBT, mean PT, and those results got published in this paper. And that is where we wrote that these results demonstrate that the capabilities of star detector, although optimized for 200 GeV center of mass energy, are suitable for the beam energy scan program. And thus the program got approved, and this is the duration where the phase 1 of the program took place from 2010 to 17. Including the 9.2 GeV beam energy, there were 10 different. This column tells us the event statistics. This is the year, and we were able to study the system having mu B from 20 to 420 MeV. I think for a single experiment or facility spanning such a large mu B of the phase diagram, this was quite unique, and for the first time for heavy ion collisions at high energies. Now, most of the results that I will show are from the star detector at RHIC. There are 2 sub-detectors which are used. One is the time projection chamber, which is kept inside a magnetic field of 0.5 Tesla. This gives us particle identification at low momentum, as well as the momentum of these particles. Then there is a time of flight detector surrounding the time projection chamber, which allowed for the particles to be identified to higher momentum. And the beam counters were used as triggers. Now, what is one of the very interesting aspect is the acceptance of the various particles that we have in the beam energy scan program. The acceptance is plotted as transverse momentum as a function of rapidity. As an example, results are shown for gold-gold collisions at 7.7 GeV, 39 GeV, and 200 GeV. It's shown for pions, kaons, and the bottom row is for protons. And you can see at mid rapidity, the acceptance is pretty uniform across all the species and for all the energies. This is very crucial when we do fluctuation analysis. Another key point in the measurement is the particle identification. So we identify the particles using the specific ionization energy loss of a charged particle plotted in the y-axis as a function of its momentum by charge. This is from the time projection chamber. And you can see at low momentum, we can very beautifully separate out the pion, kaons, and protons. Then we make use of the time of flight detector, which gives information of velocity. And when we plot 1 by velocity from the time of flight as a function of momentum by charge from the TPC, we are able to extend the particle identification to larger momentum. And all these plays crucial role in obtaining the final results from the beam energy scan program. So with this introductions, let me now go to the results. First, I will discuss the chemical freeze-out related measurements. These are based on these publications here, and one of them appeared as an editor suggestion in the Physical Review C. Now, the data which is used to obtain the chemical freeze-out parameters or the quantities related to that are the particle yields. What is shown here on the top is the dN dy divided by number of participating nucleon pair for charged pions, the middle one for charged kaons, and protons and antiprotons. Also shown here are the K to pi ratio as a function of collision energy, pi minus by pi plus as a function of collision energy, K minus by K plus as a function of collision energy, and P bar by P. And on this right-hand side lower plots are lambda by pi and cascade by pi. All these goes as input to obtain the chemical freeze-out parameters. But what you can already see is how drastically these particle ratios change in the beam energy scan regime. For example, P bar by P changes from 10 to the power minus 2 order to about close to 1. So also the K plus by K minus from around 0.4 to unity. All these changes suggest that the medium composition and properties are changing when we take data for the beam energy scan program. It's both challenging as well as interesting, as we see that there could be effects which are related to change in the baryon density of the matter when we do our beam energy scan program. Now, to obtain the chemical freeze-out parameters, we take help of a statistical thermal model. Of course, what we mean by the chemical freeze-out is where we expect the inelastic collisions to cease. Now, the statistical thermal model, we can write down the partition function for a grand canonical ensemble picture as shown here, where GI, for example, is the degrees of freedom and V is the volume. The temperature is here and the different chemical potentials are given by mu. We can obtain the yields of various particles by taking a derivative of log of partition function with respect to the chemical potential as shown here. The basic assumptions are in this model which you have used is that the hadrons and resonances are non-interacting. We assume there is thermodynamic equilibrium and two different ensembles are used to extract the parameters. One is grand canonical ensemble, the other is the strangeness canonical ensemble. The two dominant parameters which we look at is the temperature and the baryonic chemical potential. Now, first, let me show you as a representative plot how the data and the model compare. Y-axis here on the top panel is the yield of these particles shown at the bottom. The red points are data, gold-gold collisions 7.7 GeV, central collisions, also shown are results for 39 GeV. The left-hand side has the model results in blue from grand canonical ensemble. The right-hand side are from the strangeness canonical model. The deviation of the data and model are shown in the lower panel. You can see that the data and model are in relatively good agreement, both for grand canonical and strangeness canonical models. Now, the two important parameters which we extracted are shown in this plot. This is temperature, chemical freeze-out as a function of its baryonic chemical potential. And these left-hand side are the results from grand canonical ensemble. Right-hand side are the results using the strangeness canonical ensemble. Also shown as lines, and the bands representing the uncertainties are from fits to the global data. What you see first is that if we use these two different ensemble picture, roughly the temperature and the chemical potential values are of similar order. Temperature varies from about 160 MeV to 140 MeV, and mu V varies from about 20 MeV to 400 MeV. Next point to see is that the centrality dependence at each energies. The red point corresponds to central collisions, green one for mid-central collisions, and the blue ones for peripheral collisions. The temperature doesn't have much of a centrality dependence, but the chemical potential has a centrality dependence. At least it's seen in the lower energies. Now, one other interesting aspect to look at is what about the nuclei? Do the nuclei freeze out at similar properties as hadrons? That is because nuclei have binding energies which are typically of few MeV, whereas the temperatures that I talked about in the previous slide is of the order of 100 MeV. So it's interesting to figure out about nuclei production by looking if their yields can be explained by thermal model, and I will discuss later whether by the coalescence picture. Now, on the right-hand side is the plot of deuteron by proton as a function of collision energy and d bar by p bar as a function of collision energy. The dashed line are thermal model with temperature and chemical potentials that fit the hadronic yields. You can see they can explain the data pretty well. So the freeze out properties based on this model seems to be similar for nuclei and hadrons. On the right-hand side is the coalescence parameter. This is nothing but the ratio of cross-section of the nuclei, here deuterons or antideuterons, divided by the invariant yields of the nucleons to the power of their mass number. This coalescence parameter B2 is plotted as a function of collision energy. And what one finds is that there seems to be a non-monotonic variation with a minimum around 20 to 40 GeV. Is this related to some change in equation of state as we go from higher to lower energy? We need theoretical inputs in order to understand this. Another interesting point is that we find the blue points corresponds to D bars and the red points are for deuterons. And we see a difference below 62 GeV. Does it mean that the emitting source of antibaryons are larger than baryons? Again, we need some more measurements or theory in order to understand why this difference happens. So what about other aspects of freeze-out geometry? Those can be extracted from HBT-like measurements. For example, on the left-hand side is an estimate of the homogeneity region volume as a function of collision energy. That shows an interesting non-monotonic variation, although it's fairly monotonic in the beam energy scan regime, increases with collision energy. One can also extract lifetime of the system through the radii measurements. And this is shown in this figure where an input is the kinetic freeze out temperature, which is taken to be about 120 MeV. We find that the lifetime varies somewhere between 5 Fermi over C to around 8 Fermi over C. Another quantity which we can extract about the freeze out is the freeze out eccentricity. Those can be obtained from the ratios of the radii, which we measure from HBT, and as has been done by the STAR experiment in the beam energy scan program. And the results are shown from 7.7 GeV to 200 GeV. These freeze out eccentricity are plotted as a function of participant eccentricity obtained from Glauber model. If they would have been same, they would have followed this line, dashed line, which is shown in each of the panels. And they all lie below this line, indicating that the freeze out shape could be out of plane extended elliptical in shape. So what would be the broad conclusion about the freeze out dynamics in the beam energy scan program? One is that the extracted freeze out temperature is very close to the transition temperature predicted from or expected from the lattice QCD. So it seems the chemical freeze out is quite close to this transition line. Another thing is which one can infer is from this K to pi ratio. One notices that the K minus by pi minus ratio seems to increase smoothly with collision energy. Whereas the K plus by pi plus ratio, both from the data at RHIC beam energy scan program as well as the SPS program, seems to show a peak-like structure around 8 GeV. Now this data is well explained by thermal model. And if one looks back at the thermal model, one also finds a peak which corresponds to the peak of the baryon density at freeze out. So it seems that at the RHIC beam energy scan program, we have entered a region which has high baryon density. And there is change in that sense, in terms of the medium constituent or properties. Now let me move.
Bedanga, before
Yeah.
you go on, can you go back to the previous slide, the one before that? One more. There's a question from Min He. I suppose the experimentalists only measure DNDY at mid-rapidity, but the statistical hadronization model calculations assume full pore pi emission of hadrons from the source. I suspect this mismatch becomes more questionable toward lower energies, which is, while it is probably okay at top RHIC energy and LHC energy. Can you comment on that?
Yeah. If he's referring to this statistical model which explains the data at RHIC beam energy scan, it is at mid rapidity. But some of the lower energies data could be could have 4 pi. But the beam energy scan program all are at mid rapidity, and the thermal model calculations are for the mid rapidity data.
Okay, you can move on.
Okay, now let me come to the collectivity related measurements. These are based on these publications from STAR. I will try to present results from radial flow, directed flow, and elliptic flow. These are of course related through the theory calculations to the equation of state, partonic collectivity, and I will also discuss about the nuclei collectivity. It has an implication on their production mechanism. So I'll start first with the radial flow. This is the isotropic expansion of the fireball formed in heavy ion collisions. We obtain this by looking at the transverse momentum distribution of the produced particles. The transverse momentum distribution gets frozen at the kinetic freeze out where even the elastic collision cheeses. Ideally, this invariant yield of pion, kaons, protons as a function of the transverse momentum should be confronted to the full hydrodynamical calculations. And then you can extract the radial flow, the flow velocity, and the kinetic freeze out temperature. What we have done here is a blast wave model, which approximates the hydrodynamic models. Of course, it assumes that the particles are locally thermal, moving with a common velocity. Within the framework of this model, the invariant yields are given by this expression, which has two major parameters, the temperature and rho, which includes the radial flow velocity beta, and it has a profile, how the beta changes as you go from the center to the periphery of the fireball. So with this model, we try to fit simultaneously the positive and negative particles, pions, kaons, protons, and those fits are shown by these dashed lines. And then one extracts the kinetic freeze out temperature and the beta values. Those temperature and the beta values are shown here as a function of collision energy. Here is the results for the kinetic freeze out temperature. You can see based on this blast wave model, it seems to increase as you go to lower energies from around 90 MeV to about 120 MeV. If you look at the average radial flow velocity extracted from this model study, then you find that it increases as one increases the collision energy. But at the lower beam energy scan program, it seems to stay constant. Those were the results from the rate for the connection to the radial flow. Now let me look at the collectivity which one extracts from the azimuthal anisotropy measurements. So two heavy ions come and collide at non-zero impact parameter. The overlap region has, the initial overlap region has a spatial anisotropy. The constituents of the system undergoes interactions that leads to a pressure gradient which is different or larger in this direction compared to this. All these leads to an anisotropy in the momentum space. One quantifies this anisotropy by looking at the azimuthal angle distribution with respect to the reaction plane, which is a plane subtended by the impact parameter and the beam axis. If one does a Fourier transform of the azimuthal angle distribution, then one has this Fourier coefficients, which sort of quantifies or is a measure of the collectivity. For example, the directed flow is V1, which is the average over all particles, all events, cosine of phi, where phi is the azimuthal angle with respect to the reaction plane angle. And V2 is called as the elliptic flow, which is average over cosine 2 phi. And if V2 equal to 0 would correspond to a free streaming case. So let's see what are the interesting results first from V1 from the RHIC beam energy scan program. So what we do is we measure this V1 as a function of rapidity, and the quantity of interest is the slope of this V1 versus rapidity. And that is what is plotted in the y-axis, slope of V1 versus rapidity at mid rapidity as a function of collision energy for antiprotons, protons, and net protons. Let's concentrate on the net protons. What we see is that there is a non-monotonic variation of this slope as a function of beam energy. Not only that, there is change of sign from positive values at lowest beam energy scan energies, going to a minima with a negative value, and then again rising back to a positive value. Models like URQMD fails to explain the data completely. A minimum in such an observable has been predicted to be sensitive to equation of state in certain models. And hence we think that this data provides information about equation of state of the system, and the theory calculations are needed to extract information. We then moved on to add several other particles to these measurements. For example, lambda, phi, kaons, and pions. Let's look at this lower panel. What we find is that the net lambda follows very closely the net protons. So we can say that the non-monotonic variation of the directed flow slope as a function of collision energy is seen for net baryons. Whereas for mesons, it seems to show a monotonic variation. Now, using this data, we can test several coalescence sum rules, which are discussed in this paper and shown here. Coalescence mechanism seems to work well at higher energies. At lower energies, we have to actually look at how the transported quarks play a role. Different variants of this coalescence mechanism explains different part of the data. One variant explains comparison of the red and the black, shows one variant of this coalescence picture, which explains at the higher part, energy part, fails to explain at the lower energy part. Another variant of increasing the contribution from the transported quarks seems to explain the lower energy part better, and not so in the higher energy part. You have to compare the blue with the black. Now let's come to the elliptic flow measurements. And let's look at this left-hand side plot. These are elliptic flow measurements as a function of transverse mass minus mass of the hadrons. A variety of hadrons starting from pions to omega and phi are shown here. All the data shown in gray are for baryons and the red are for mesons. 7.7 GeV gold-gold collisions to 62.4 GeV gold-gold collisions data has been presented here. For 3 different collision centrality, 0 to 10% central small impact parameter, 10 to 40% mid-central, and peripheral collisions 40 to 80%. Let's look at this middle panel. You can see distinctly around the mid MT minus M0, there is a distinct difference between baryons and mesons, red and the gray bands. And that is the basis of the number of constituent quark scaling. This difference gradually reduces as you go to lower energies, indicating that hadronic interaction seems to be dominating at lower energies compared to those at higher energies. So the NCQ scaling, as we saw at the RHIC top energies, is no longer holding at the lower energies. This is one of the key measurements of the turn-off of the effects that we saw at the RHIC top energy. In addition, we saw at the RHIC top energies that the particle and antiparticle V2 are of similar magnitude. But what we see here, and as is shown in this figure, the difference between V2 particle and antiparticles, especially for baryons, seems to increase as you increase the baryonic chemical potential. It has a linear dependence, both for protons and the lambdas. Pions, in fact, it goes in the other way. Now, all this suggests that the NCQ scaling, like the ones which we saw top energy, is no longer holding, but it also gives some interesting measurements, which tells us that we are seeing effects of perhaps difference in baryon densities as we dial down the lower energies. In fact, models which take mean field approach, where things like vector coupling, which are related to baryon densities, are put in, seems to qualitatively explain this data. Now, let's look at the elliptic flow of the nuclei. The idea here is to see if the elliptic flow of nuclei scale with the mass number. So for that, what is plotted here is the V2 of nuclei divided by the mass number. The nuclei are deuteron, helium-3, and triton. The results are shown for 7.7 GeV to 200 GeV. They're also compared to the nucleon or the proton and antiproton V2. And then the function is fitted to this proton V2, and the ratio of this to the nuclei V2 is taken in the lower panel. And you can see the fact that the ratio is 1, V2 scaled by the mass number, plotted as a function of PT scaled by the mass number, when divided by the V2 from the nucleonic contribution, is around unity, suggest that this mass number scaling holds, which qualitatively tells us that the nuclei, according to this observation, is formed through coalescence of the nucleons. Another way to look at this picture is to confront the data of V2 versus PT of these nuclei like deuteron, helium-3, and triton with a coalescence model incorporated within a transport approach. Those are shown by the gray bands, and they seem to explain the data, especially up to at least 11.5 GeV, relatively nicely, validating that in this observable, the coalescence picture seems to be holding. So what are the conclusions related to collectivity? We have a wealth of data coming from collectivity measurements, through which we can test various coalescence mechanisms and understand medium properties. All of these data seems to indicate that there could be dominance of hadronic interactions over partonic interactions. There are indications of switching off of this NCQ scaling at lower energies. We saw non-monotonic variation of net baryon directed flow slope as a function of collision energy. What I didn't discuss is also there is non-monotonic variation of V3 square as a function of collision energy. We have seen differences in collectivity of particles and antiparticles. These may be indicating to sensitivity to the medium properties as we dial down the beam energy. In BES2, we would like to have precision measurement of phi meson flow. Why? Because they freeze out early and have small hadronic interaction cross-section. Large part of their collectivity should be developed at partonic phase. Here is an example of what I'm trying to say. The average V2 as a function of collision energy for phi and proton, why I chose proton is because they have similar mass, is shown here as a function of collision energy. You can see that the phi meson follows the proton and starts to drop off, although statistical error bars are large, and BES2 measurement will confirm this deviation. Drop in phi meson V2 where phi freezes out early would indicate small contribution coming from partonic phase. To substantiate further this sort of picture, we have 3 bands corresponding to V2 from AMPT having string melting, partonic interaction with 10 millibarn cross section, 3 millibarn cross section, and only hadronic interactions. And that seems to follow that picture. We have now theoretical attempts looking at the data to understand the equation of state and extract the eta by S. 2 such calculations are shown here, and the eta by S extracted from these theory calculations suggest it seems to increase as you dial down the energy in the BES regime. So these were some of the findings from the collectivity. Now let me move to the criticality. These are based on these papers. Now, a star experiment developed this observable of higher moments of net particle distributions, which could be related to conserved quantum numbers such as net charge, net strangeness, or net baryon number. This was actually developed in collaboration with theory colleagues at INT workshop in 2008. It was soon realized that these higher moments are proportional to the correlation length of the system to their powers. And the power seems to increase as you go to higher orders. That means higher moments are more sensitive to the physics of, like, for example, critical point. This is specifically important because heavy ion collisions have finite size and time effects. Another interesting thing which we figured out is we can measure product of moments in experiments, and those could be related to the ratios of susceptibility which can be computed in theory. So a connection between theory and experiment can be made. People have gone on to extract freeze-out temperatures and test thermal equilibrium pictures using higher moments. The first such measurements came out from STAR by looking at the event by event net proton distribution as shown here. Number of events as a function of number of protons minus antiprotons. Then one can extract from these distributions the mean, the sigma, the skewness and kurtosis, and then look for the physics behind this in order to address the physics of critical point. Now, what do we expect from these higher moments? I've taken one particular model. Of course, maybe the details of this, Misha Stefanov will be discussing on 11th August in this series. I will just briefly tell that what he suggests is that if the critical point is close to the freeze-out line, then looking at higher moments like kurtosis, this is normalized as a function of beam energy. As you come from higher energy to the lower energy, one would expect an oscillating pattern. Of course, the exact shape and location of this all depends on where is the critical point and how far is it from the freeze-out line. In the end, we may not be able to tell about a critical point, but we could address a critical region, the physics of critical region. And this is a non-monotonic variation of higher moments is what we are looking for at first as an experimental signature. So before I go to the net proton results, let me first tell about the two other measurements which STAR did, net charge and net kaon. Net kaon being proxies of net strangeness. The net kaon kurtosis times variance and net charge and net kaon kurtosis times variance are shown in the upper and lower panels respectively as a function of collision energy. Red points are 0 to 5% gold and gold collisions, and the open black square are 70 to 80% gold and gold collisions. What we find from the net charge and net kaon measurements with large statistical and systematic errors, we do not see a obvious energy dependence for the energy range which we have measured. The statistical errors are especially large for net charge and then to a lesser degree to net kaons, and then you will find lesser degree to net protons because they depend on three aspects of the net particle distribution. The width of the net particle distribution, m is the order of the moment, the event statistics given by n, and also the efficiency of detecting the particles. All these decide the statistical uncertainties, and that turns out to be large for net charge as the widths are larger. Now let me go to the net proton results. So these are the event by event net proton distributions for 9 different collision energies. Y-axis is normalized to number of events. These are for gold-gold collisions, 0 to 5% central, transverse momentum range 400 MeV to 2 GeV, mid rapidity 1 unit. What you see is that the mean of this distribution as well as the width seems to increase as one goes from higher energy to the lower energy. These could be related to effect of baryon stopping. From these distributions, after correcting the efficiency and acceptance, we obtain the moments and or the cumulants. And then we look at the product of these moments. What is shown here is in the first panel is sigma square by mean of net protons. All the data shown are for 0 to 5% gold-gold collisions at mid rapidity. This is sigma square by mean. Middle panel is skewness times sigma, and this panel is kurtosis times variance, all plotted as a function of collision energy. The scalum or the Poissonian expectations are shown by the dashed line. Now, we are interested to see whether there is any non-monotonic variations in these observables. So what we do is we fit these distributions to a polynomial, the best fit that we get, and then look at its derivative. If the derivative changes sign, then it's a non-monotonic variation. What we find is sigma square by mean, the derivative values all stay positive. It's non-monotonic to a significance, it's monotonic to a significance of 3.4 sigma. Similar exercise for S sigma tells us that it's non-monotonic at a level of 1 sigma. But as soon as we go to a higher order moment, now this was second order, third order, now we go to higher order moments, which involves kurtosis, we find it's non-monotonic, derivative changes sign, and it's at a level of 3.1 sigma over this beam regime. Remember, the theory tells us that higher the order of moment, more sensitive is it to the physics processes we are looking for. So the higher order cumulants are sensitive observables. Now let's do a comparison with model calculations. This is again the S sigma as a function of collision energy, kurtosis times variance as a function of collision energy. Let's look at this plot. And these data are compared to transport model calculation. This is URQMD. And hadron resonance gas model, grand canonical ensemble. This is consistent with unity. They do not explain the data. They are actually monotonic in variation. Now, the statistical errors are large at lower energy. That's why we are doing the beam energy scan phase 2. We expect at the end of this program, the uncertainties to be at the level as shown in the green band. And our fixed target program will help us measure this region shown by the blue arrow. And those are very crucial measurements in order to get the full picture of the non-monotonic variation of kurtosis times variance as a function of collision energy. Now let's look at a different way of comparison with the model. This is data-driven approach. Skewness times sigma as a function of mean by variance. Now the data for central gold-gold collision are shown in red. This line corresponds to S sigma equal to m by sigma square. Hadron resonance gas model follows it. URQMD also follows to some extent and then deviates. Data deviates from both these models quite a bit and are actually in relatively good agreement with a lattice QCD inspired fit, indicating we are dealing with strongly interacting QCD matter. There are other measurements which we did on fluctuations and correlations, which could be related to the criticality aspects. Some of these are shown here. I will not go into details, but I will just highlight some aspects. Like on this left-hand side, we have this off-diagonal measurements of correlations between charge and kaon and charge and protons. And you can see that the data as a function of collision energy are all above unity, and model calculations are either close to unity or below. Models are not able to explain this second order off-diagonal cumulants measured from data. We also look at rapidity correlations between protons, antiprotons, and proton and antiproton. The interesting trends at mid-rapidity we see are some kind of anti-correlations. From the mean PT correlations, they show a monotonic increase with collision energy, and so also the new dynamic for kaon pions, they seems to show a monotonic increase for the collider energies. So these were some of the other fluctuations and correlation measurements which STAR has come up with. So on the chirality part, I would conclude by saying that we have seen some non-monotonic variation of kappa sigma square of net proton distributions, central goal-goal collisions with collision energy with 3 sigma significance. The statistical uncertainties at lower energy, especially between 7 points at 7.7, 11.5 is high, and that's the focus to increase the precision in beam energy scan phase 2. Now I will move to the last part, measurements.
Bedanga, for your information, 10 minutes to 1 hour.
Okay, thank you.
Yeah.
So I will discuss about measurements related to chirality. These are based on these publications. So before I move, 2 interesting initial conditions are very crucial for such measurements. When 2 heavy ions at non-zero impact parameter come and collide, then the participating matter is imparted a large angular momentum because of this torque. Then this angular momentum is expected to be perpendicular to the reaction plane, subtended by the impact parameter and the beam axis. These nuclei consist of protons, which are charged particles moving at relativistic speed, and that would give a large magnetic field to the system. This magnetic field is also perpendicular to the reaction plane. Both these effects are important for chirality and polarization related measurements. Now, just to give you an idea about how large are these magnetic field and angular momentum, here is a calculation of the angular momentum J in units of h bar as a function of the impact parameter of collision, gold and gold collision at 200 GeV. There are small values for central and peripheral collision, but at mid-impact parameter or mid-central collision, they could be as large as 70,000 to 80,000 h bar. Remember, this angular momentum is a conserved quantity. Its effect we expect to feel throughout the evolution of the system. The magnetic field here is plotted from this model calculation for various impact parameter of gold-gold collisions at 200 GeV in units of MeV square as a function of the time. It does rapidly die down with time, but the initial values as large as of the order of 10 to the power 18 Gauss. These are 2 crucial initial conditions that we experience in heavy ion collisions, and we try to see if we can see some observable consequences of this. One of them is related to the chiral magnetic effect. The observable, which is expected to be sensitive to this, one of the observable is this 3-particle correlation, where phi1 and phi2 are the azimuthal angles of 2 charged particles, and this is the reaction plane angle. And STAR has done a very systematic measurement of this gamma variable as a function of collision centrality from 7.7 GeV to 200 GeV, also shown our results from 2.76 TeV. What is interesting is that the red points are this correlation for same charge and the blue points are for opposite charge. And you see there is a distinct difference. And as you dial down the collision energy, the difference vanishes. Now that again indicates that perhaps hadronic interactions are dominating at lower energies. Now this difference that you observe at higher energies could be consistent with the trends expected from chiral magnetic effect, although there are alternate hypotheses which exist. Therefore, a dedicated isobaric run has taken place at RHIC to give more clarity to this picture. Just to emphasize about some changes are happening as we go down in beam energy. This is the difference of this correlation between same sign and opposite sign as a function of collision energy for 3 different centralities. Let's look at this middle panel, and you can see that these differences go down as you go to smaller energies. And remember, phase 1 of the beam energy scan was looking for such turn off effects. Another interesting measurements which we reported could be related to chiral magnetic wave. The observable is look for V2 of charged pions as a function of the charge asymmetry in an event, that is difference in pi plus, the positive negative charge particles to total number of charge particles. This difference, when plotted as function of asymmetry, you have a slope, and a non-zero slope could be related to this phenomena. And this slope is what is plotted here in y-axis as a function of centrality from 7.7 GeV to 200 GeV, and we do observe a non-zero slope. This could be related to this phenomena, but recently it has been suggested to look at not only the V2 difference, the slope of V2 difference, but also V3 difference. And only if there is a difference between the slope associated with V3 difference and V2 difference, you could perhaps say that there is a chiral magnetic wave-like effect. Now, coming to the last part of this chirality, here are the very interesting results from STAR experiment on lambda polarization. These polarization values are extracted by looking at the angular distributions of the protons coming from the lambda. These angular distributions then give us a value of the polarization. This polarization, by the way, is proportional to the quark polarization. What we very interestingly see is that the polarization value seems to increase as we decrease the beam energy. These polarization could be related to the vorticity, the thermal vorticity of the system, and in a model estimate of this is of the order of 10 to the power 21 per second, indicating that we have a rotating matter formed at this RHIC, beam energy scan energies. Another interesting effect of this large angular momentum could be arising because of the spin orbital angular momentum interactions. So how does one get access to that? One looks at the angular distribution of decay daughters of vector mesons. Remember, vector mesons are spin 1 particles. So what one does is look at a plane, for example, plane subtended by the beam axis and the impact parameter. This is the reaction plane. Then go to the rest frame of the vector meson. The decay daughters are back to back. Look at the angular distribution of one of the decay daughters perpendicular to this reaction plane. And that angular distribution is given by this expression, where ρ00 is the 0th element of the spin density matrix, which is a 3×3 Hermitian matrix. Now, this ρ00 basically tells us what is the spin state of this vector meson. It's a spin 1 particle. It can stay in a state -1, 0, or 1. The probability that it is in a spin state 0 is ρ00. All states could be equally probable in absence of interaction with angular momentum. So ρ00 will be 1/3. Then this distribution, if I substitute 1/3, the angular part drops off. It's uniform. Any deviation due to spin orbital angular momentum interaction will make this distribution non-uniform and ρ00 deviate from 1/3. And that is what is measured at RHIC and LHC. And there are some deviations seen, and this could be related to spin orbital angular momentum interactions. So on the chirality related, we have measurements which are sensitive to chiral magnetic effect, measurements which are sensitive to chiral magnetic wave. We have now rich physics associated with the polarization measurements, and these have led to significant new developments in theory in terms of relativistic spin hydrodynamics and magnetohydrodynamics. So what are the overall conclusions? I think 20 years of STAR running, STAR has been pushing the tests of QCD at high temperatures and densities to its limits. What we set out to see if there are some non-monotonic variations in observable which can say about something about turnoff of the signals that we saw at RHIC energies or sensitive to the equation of state. We find from experimental measurement point of view, there are some such trends when we measure the transverse mass, average transverse mass as a function of collision energy, or V3 fluctuations as a function of collision energy, or difference in HBT radii as a function of collision energy, or product of moments of net proton distributions as a function of collision energy, or slope of directed flow of V1 of protons as a function of net protons as a function of collision energy. These are some striking measurements which has come out from the beam energy scan program showing non-monotonic trends. We have also gone on to see that some turn-off of QGP-like features from the experimental data. For example, nuclear modification factors at high PT, highest up to which we could measure, seems to go from net suppression to net enhancement. Or the turn-off of the NCQ scaling, as I discussed, baryon-meson separation seems to be vanishing as we dial down the lower energies. It also added to understanding the properties of the medium. This slide just summarizes some of the values which came up from RHIC and especially from the beam energy scan program, like initial temperatures, the chemical freeze-out properties, the radial collective velocity, homogeneous volume, system lifetime, system properties in terms of eta by S, Q hat, and diffusion coefficients, and vorticity. These are some of the contributions which has come out from this program. What we can do quickly in 2 slides on the BES phase 2 and fixed target is improve the precision and increase the range of the measurements. Using detector upgrades, we can go to higher rapidity with particle identification and better measurement of centrality and even plane through these upgrades. We will be focusing on the lower part of the beam energy scan program, increase the statistics by an order or 2 orders so that we have precision measurements in high baryonic chemical potential region of the phase diagram. The fixed target program will extend our measurements to a strikingly large μb of about 750 MeV, making the RHIC beam energy scan program spanning the phase diagram to a largest range in μb by a single experiment. So I will end by saying that the beam energy scan program has provided systematic study of the phase structure of the QCD phase diagram. There is still some amount of work to be done, which will be achieved through the phase 2, trying to look for the signatures of the true phase transition or critical point, understanding of properties of high baryon density, rotating QCD matter under magnetic field, and of course, some interesting results are expected on nuclei, hypernuclei and exotic nuclei formation and properties. This program is highly complementary to research programs at CERN and ones which are coming up at FAIR, NICA, and JPAR. In fact, we can, the higher moment measurement specifically gives us an opportunity to test thermalization of the distributions that we measure in heavy ion collisions. So this is the last slide giving us an overall picture which has come out from the beam energy scan program. Our goal is to look at the phase structure of the QCD phase diagram. We have been able to throw light on the properties at chemical freeze out and address issues of thermalization. Through collectivity measurements, we have been able to address equation of state related aspects. We have measurements which can address those, and as well as properties. We have very interesting novel QCD phenomena which can be probed, like chiral magnetic effect, chiral magnetic wave, and some very interesting polarization measurements. We are making progress on criticality measurements. We are highly productive, and there is great link with the existing CERN program as well as the upcoming FAIR and NICA. So with this, I will thank again the organizers for giving this opportunity, and thanks to all the star collaborators without which these results would not have been possible. Thank you very much.
Thank you, Bedanga, for this comprehensive talk. So now we are in a question session. I would suggest whoever wants to ask